Okay, finally, the eigenvalue equation on the unit disk. Of course, we are once again in polar coordinates. We're going to go for zero boundary conditions. Zero boundary conditions. That condition will quantize the spectrum in a very interesting way, in the way that you haven't encountered until now. Until now, all of the problems have been so specially chosen that we just had integers or multiples of integers or sums of integers. It's just worked very nicely. It will no longer work in this case. Let me draw the unit disk. You will also notice that I put a minus sign in front of the eigenvalue. So I'm kind of redefining what lambda is. Okay, so this way, all of the eigenvalues will come out positive. Of course, eigenvalues of the Laplace operator are negative for reasons that we'll discover today in our linear algebra class. Okay, but by putting a minus sign, we'll have a square root of lambda in our discussion. So without the minus sign, we would have had to have square root of minus lambda, which just doesn't look as nice. So I put a minus lambda here. So I think the calculation itself is quite straightforward. We know what we're going to do. We're going to separate variables, and then we'll see the equations that are presented. So let's go ahead and do that. I think I can skip most of the intermediate steps. We'll have okay, now keep in mind this is the eigenvalue. We're about to be presented with sort of an intermediate eigenvalue problem. You'll see that in just a moment. So that won't be the eigenvalue of the eventual problem. Just keep in mind that the eigenvalue of the eventual problem is lambda, maybe minus lambda. Okay, let me multiply both sides by r squared. Okay, so we have a left-hand side that depends only on r, and a right-hand side that depends only on theta. Everybody's with me? I think it's okay. We've done this sort of thing 4 or 5 times already. So each one must be a constant. And we know what's happening here. This will be sines and cosines. This is the angular part of our function. It'll have to be periodic. So sines and cosines. And because of this minus sign here, it will be n squared, a positive number. A positive number. So we have our own little eigenvalue problem here for the angular part. And of course, it ends up being, and from here we know that theta is a linear combination of sines and cosines of n theta. And so the quantization that we get from this is that n must be a positive integer. Well, of course, not only that, for completeness sake, let me just write down what we get. But perhaps most importantly is that, well, I can't say what's more important. N is an integer. If n was not an integer, we wouldn't have a continuous function when we came back to the beginning. Okay, so n is an integer. So here we end up with the following equation. Let's be careful. That's our equation. So this is called Bessel's equation. That's our Bessel, the stellar parallax Bessel. Bessel equation. Let's ask the most fundamental questions about this equation. Is it linear?
Yes.
Yes. And this is just about the right amount of time that it should take you. Right? It's an eyeball question. You eyeball it and it's like, yes, it's linear. Here is the second derivative, the first derivative, the 0th derivative, all enter into the equation linearly. Does it have constant coefficients? No, it does not. So interestingly, running ahead by just one step, what are the solutions to this equation? R to the n, you can try R to the n, it will not work. R to any power will not work. An exponential function will not work. A combination of trig and exponential functions will not work. In fact, no combination of elementary functions whatsoever will work. There are no elementary functions that satisfy this equation. And until now, from examples, you may have gotten the false idea that somehow you always end up with some combination of exponentials or polynomial functions and so forth. But you can see that very innocent elements in a linear equation can throw that right out the window. Right? This is a pretty clean equation as far as equations are concerned. Right? So the coefficients are very uncomplicated, but it takes that little to eliminate solutions as combinations of elementary functions. So people had to think of new functions that would be solutions to this equation. And they're called, can you guess? They're called Bessel functions. Bessel functions are solutions to this equation. Now, how is it helpful to say that this equation doesn't have solutions in elementary functions? So we're going to invent two more functions and call them Bessel functions. And there you go, now it has a solution. But how do you evaluate a Bessel function? Right? It's kind of useless unless you're able to evaluate it. Well, in the 19th century, people had brilliant techniques, mostly what you would call calculus 3, calc 3 techniques, infinite series. You can find solutions of this equation as infinite series. You can find them as very special integrals with certain parameters in them. You can find books this thick on Bessel and like equations. This theory was extraordinarily well developed. Not only could they evaluate these functions, but they knew a ton of their properties through the coefficients, through some of the other relationships that these functions satisfied. People knew a ton of things about Bessel functions, of which I know, I would hesitate to say 1/100th of 1%, because I just typed Bessel J into Mathematica, and to me it's like an elementary function. What's the difference for me between typing in sine of x and typing in Bessel J, as these functions are known in Mathematica? No difference at all. And so I can afford to know nothing about them. And if I have to take derivatives, Mathematica does it for me. But mathematicians had everything figured out. They figured out that the derivative of one of these Bessel functions is a linear combination of another two. Okay, so I'll present these Bessel functions in just a moment. Why did I say two Bessel functions? Well, that's because it's a second order linear differential equation. And so there have to be, for a given n and lambda. This is all for a given value of n and lambda. And think back for just one more moment and realize that we know that n needs to be an integer, but we don't know anything about lambda yet. So lambda is still an unknown, which will of course be determined by the boundary condition. That's the moment these constants present themselves to us, is when we actually have to satisfy a boundary condition. And so for any given n and lambda, there are two linearly independent functions, with the help of which we can write out as a linear combination all possible solutions to this problem. Okay? So we're going to get to those in just 1 second. But I think what's a little bit upsetting about this equation is that there are two parameters. That means that this would be a two-parameter family of functions. We have to solve this equation for any given integer n, and then supposedly for any given lambda, and then somehow from whatever we obtain decide what lambda needs to be so that the boundary conditions are matched. So that's unattractive, but fortunately you can make lambda disappear. So anybody who is trained in the art of manipulating equations and doing variable substitutions would see that from just how lambda appears, from how each one of these terms is in a way homogeneous if you look at units. I don't want to go too far into this. I'll just show you the substitution that worked. I probably would have been able to think of that substitution after about 2 days of work and trying this and that. I think I would have finally seen what to do. But basically, I will make lambda disappear by looking for solutions in the following form. Let me kidnap this portion of the board. I will say with a lot of foresight is let me look for r. I'm just going to rescale my variable by square root of lambda. And when I do that, you will see that square root of lambda will disappear from everywhere. It will, in a way, get absorbed into r. So here's how I'll do it. I'll call my new function j, and so I'll be looking for a function, for an equation for j, where I'm basically scaling r by square root of lambda. So let's see what r prime will be. R prime and by another application of the chain rule, the second derivative when it comes to changing variables, you have to be very, very careful, always reminding yourself what's going on. Right now, we don't have a rich enough example to illustrate what I'm trying to say. But if you ever take tensor calculus, that's all we'll talk about for the first 3 weeks. The art of differentiation is when I learned that I had no idea how to differentiate things formally, generally speaking. I could take a derivative of any given function, but things like that would trip me. And they would still trip me if I tried to do them fast. So there is a special kind of awareness that you need to develop that will really serve you well. So then, in terms of j, this becomes, if I plug it in here, we find that this is lambda r squared j double prime. But remember of what? I'll write it of square root of lambda r. I can see that I'm running out of space. Plus, plugging this in here, we get and do you kind of see what's happening now? If I were to now call this variable rho, the equation that I end up with is and it's the exact same equation, except lambda went away. And it's j of rho in each time. So it's clean in terms of rho. So the stretching of coordinates, actually maybe a shrinking of, depending on which way you're looking at it, makes lambda go away. And so actually it's this that's called Bessel's equation. It's very nice that you're able to go from a two-parameter family of equations to a one-parameter family of equations. And it's the solutions to this equation. They're called Bessel functions. And because it's a second-order equation, there are 2 of them. Let me write down not what they are, but what they're called. All right. So what I'm going to do now is rename rho back to r. That's what makes these variable substitutions so confusing, is that you play with letters a lot, and you can very easily make a mistake if you're not fully in control of what you're doing. You cannot rely on the notation telling you what the right thing to do is. If you rely on the notation, you will make mistakes. I can't explain it any better than I'm doing it right now. You should just go ahead and find yourself in this situation and make a mistake and then take 2 days to find it. There are famous examples in history of famous mathematicians making mistakes and variable changes, essentially, and then taking years to find them. You have to be very, very careful. I usually don't prepare for these lectures. But in this case, I knew that I had to be careful. So I practiced this. It took me 30 minutes to figure this out. I knew it was a rescaling by square root of lambda, but to actually go the right way, I probably tried 4 or 5 permutations of what I could have done and notation I could have used, and the first 4 were wrong. Didn't make it simple or clear, or in some cases correct. So it's not as easy as I just made it appear. It's very tricky. You have to do a lot of talking to yourself to get through these calculations. So whenever you see somebody do this as effortlessly as I just did it, it's basically a lie. These are very difficult. You always have to do them very slowly. And like I said, keep talking to yourself. What are you doing? Are you substituting? Are you expressing one function as a function of another? When you say prime, you have to be very careful what prime means. That this is, when you say prime, that it's the derivative with respect to its own argument. And this is the derivative of j with respect to its own argument, for which we substituted square root of lambda r, and so forth, those kinds of conversations. Okay, but now renaming back to r, we're ending up with classical Bessel equation. Classical Bessel equation has 2 solutions, j sub n and y sub n, as they're called. J sub n and y sub n. This equation has a serious problem. And that's this coefficient of r squared multiplying the highest derivative. Whenever you have something multiplying the highest derivative that equals 0 at a point, and this equals 0 at r equals 0, you're guaranteed to have a problem there. Because remember, we discussed our treasure hunt way of solving ordinary differential equations. Well, from the treasure hunt point of view, you can't even start solving this equation at 0, because at 0, you're not even able to express what the second derivative is. So it's a big problem from that point of view. So you might say, okay, I'll start at 1 and I'll move backwards. You can do that, but if you start at 1 and you'll move backwards, because you're dividing by r squared, you'll realize in the treasure hunt sense, your derivative is getting larger and larger and larger and finally blows up. So there's a strong indication is that one of the solutions to this equation will blow up at 0, and that's the y's. And the other solution won't blow up at 0, and that's the j's. At least you can choose it that way. So you can find one that doesn't blow up at 0, and one that does. So, but one always will. So it will always be, let's say, a of this plus b of this. And I believe, well, let's put of r, why not? Okay. These are called, I believe, I'm not sure of the terminology, Bessel functions of the first kind, Bessel functions of the second kind. And this is our first encounter with functions that are not polynomials and not sines and cosines. But these are polynomials that sort of feel in some ways like sines and cosines. I'll draw a few of them. So J0, right? There's a pair for each n. So these guys all blow up, so I won't draw them. But J0 looks like this. Okay, and the further out it goes, the more like a cosine it becomes. And these segments between the roots become more and more regular. And out to infinity, they're almost all equal to each other. Okay, and then J1, all of the rest of them, starting with n equals 1, start at 0. And I believe follow, I don't know if it goes up or down. You could choose either way. You know, maybe look like this. And then another one that's, you know, they begin to look like sines and cosines. Okay, that's not surprising, right? Because it's sort of like, you can think of it as a rectangle which has sines and cosines, right? But kind of folded on itself like this, a little bit. Remember, we considered a rectangle, and then we considered a really long rectangle. So now imagine that really long rectangle and close it on itself. As a drum, it probably won't sound that much different. You know, so that's why out there, I'm not really explaining it. I'm just trying to connect them in some ways. But it's not too surprising that they're not sines and cosines, but at the same time begin to look like sines and cosines. Okay, so that's the solution to this equation. But we're interested in a solution to this equation. So our solutions will be these Bessel functions scaled by square root of lambda. Square root of lambda. And we have to reject the y's because here we cannot afford functions that blow up at 0. So we only have the j's. So the solution to our equation, well, it's also called u. But this is u sub n, I'll call it. The solution to our eigenvalue equation, r and theta, equals. So the angular part is once again just our perfect harmonic function, sines and cosines. Not harmonic, what am I saying? Sines and cosines, harmonic in a different sense. This is just our familiar sines and cosines. But the radial part is now this. We still haven't answered the question, well, what are the eigenvalues? We still have not satisfied the boundary conditions. Well, now it's time to satisfy the boundary conditions. Lambda needs to be such that this equation has 0 when you plug in r equals 1 for all theta. So what is lambda? Let's consider n equals 0, which is your pure radial solutions. E to the I n theta is 1, so u of 0 is actually a function of r alone, and it equals. And when we plug in r equals 1, this needs to be 0. So the equation that we end up having is j0 of square root of lambda equals 0. So what is square root of lambda? It must be the first root of j0. It's whatever, pay attention, it's whatever this value is. That's why the roots of the Bessel functions are so important. And that's why previously we had integers, because those integer values are the roots of sines and cosines, right? The roots of sines and cosines are n pi for sines. The roots of sines are n pi. But for Bessel functions, we're not so lucky because they're not such regular functions. So it's whatever the roots are. So the eigenvalues of the Laplace operator are minus, remember that minus? You don't remember it anymore. Oh, well, that's the Bessel function. Okay, I don't have the Laplace eigenvalue equation here, but there was a minus. Remember this minus. So the eigenvalues on the unit disk are the roots, are minus the roots of the Bessel functions squared. Okay? And that's the spectrum of the Laplace operator on the unit circle, now complete.